Any questions before we begin? So for a second, I'll probably give you the exam grades next Monday. But hopefully well. I'm sorry to cry. I think the score is good. So um, today, what do we have to talk about? So is when orthogonality or like trying to find vectors that are perpendicular to one another. But that's a little bit different from the stuff we have been doing. We got eigenvalues and eigenvectors, but in a couple of lessons, like we'll put the two concepts together. So let me give you some reminders about orthogonal vector. So that actually involves the dot product, which I had briefly mentioned at the beginning of the course. I don't know, yeah, how much you remember it, but let me give you the basics. I mean, this is like an operation that's studied in multiple courses, like multivariable calculus, also in your physics classes. But the idea of the dot product is that u dot v, which is called the dot or scalar product of u and v. Well, that is basically the product of the length of the vectors times the cosine of the angle between them. Okay. So I don't know if I had told you this, maybe I did or not. This is the length of the vector, or also called or magnitude or norm. Um, hopefully this looks familiar. So that's the dot product. Now, if there was like this formula, and there are two things that are important about the dot product that we'll use. One was, or three maybe. The first one was the formula, an alternative formula for the dot product. So the idea is that if you have some entries like u1, u2, u3, up to un, let's say that the vectors have n entries, and these like v1, v2, up to vn, then u dot v plus like u1 v1 plus u2 v2 plus u3 v3 plus blah 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 un. Yeah. So the way in terms of the entries, how the dot product is computed is pretty easy. You just multiply the corresponding entries and add them up together. So just to give you an example, with 4 entries, right? If the vectors have been 1, -2, 3, 0, and v had been like, I don't know, 3, 5, 0, 2, then the dot product would be 1 times 3 plus -2 times 5 plus 3 times 0 plus 0 times 2, right? And that gives you 3 minus 10, which is -7. Okay. So again, I think some of this I said before in the past, but just as a quick reminder, because it's not something we have used too much up to this point, right? Which I make it say the parts are good. So here are like the two most important properties of the dot product that we need to use for today. So let me write it down. So here are some two key properties. The first one, which is actually pretty useful, is what's the dot product of a vector with itself, right? What do you get in the formula?
Magnitude of u squared.
Yeah, the only thing that you can say in this case is that if u and v are the same, then the angle is zero between them, right? Because they're the same vector. So a cosine of zero is one. So the important thing is that the dot product of a vector with itself is the magnitude, like the length squared. So that's very useful. You'll see why in a second. And the other important property is that what if you had two vectors which are well, already feel it. If two vectors had their dot product equal to zero, right? If you see like this formula, well, I'm assuming that neither of them is the zero vector, but we don't care too much about that anyway. But if the dot product of two vectors is zero, then you are having this set equal to zero, and if their lengths are non-zero, that means that the cosine of the angle has to be zero. And the way, I mean, for cosine to be zero is for, say, the angle to be 90 degrees. So they're basically, it could also be 270 degrees. It's just that by convention, the angle between the two vectors is between 0 and 180. But in any case, cosine of zero is like when it's 90 or 270 or whatever, and in that case, like the vectors would be perpendicular. So what I'm trying to say is that if the dot product gives you zero, u and v are perpendicular. In this class, in many places, it's common to call perpendicular vectors orthogonal. So that's why I'm calling this orthogonality. So also known as, also called orthogonal. So a synonym for saying that the two vectors are perpendicular is to call them also called orthogonal vectors. Is that making sense? So far, so good. Any questions about this? So again, the idea is that the dot product, that's actually for us, like the most important thing that we will use the dot product for is that if the dot product of two vectors is zero, that meant that the angle between the vectors was 90 degrees. That making sense? Any questions? Okay, so how are we going to use this today? So the idea is that up to now, we had like a vector space. We were trying to find like a basis for a vector space. That has been our goal most of the time. As I mentioned, given the same vector space can have several different choices of bases. So there's nothing unique about the choice. So you could find a basis, and I could find a different basis, and another person could find a third basis for the same vector space. So there's like a lot of freedom of how you can make those choices. So now we're moving in the direction of like giving more conditions on what we want the basis to look like, so that it becomes like slightly more useful. Okay, and that leads us to the concept of an orthonormal basis, which is still not unique, but it is a lot more like has more conditions. Like there are like less choices in a sense than just like a random basis for a vector space. And you'll see in a second why that's like a useful notion. So let me talk about so if you have a vector space where if V is a vector space, and V1, V2 up to Vn are a basis for V, form a basis for V. Okay, so let's say you found somehow a basis. We'll say that this basis is orthonormal if two things happen. This basis is called an orthonormal basis. If two things occur. The first one is that each vector of this basis has length 1. So that's what is called usually a unit vector. So each vector in the basis has length 1. So D I for I equals 1 to n. So V1 has length 1, V2 has length 1, V3 has length 1, so on. Each vector of the basis has length 1. And the second condition that's useful is that if you pick two vectors of the basis which are different, then they are mutually perpendicular. So let me write that down. I need more. Um, any two vectors of this basis are perpendicular of this basis are orthogonal or perpendicular to one another. So what I'm trying to say here is that if you choose a vector, one vector from this collection, and you choose another vector from this collection, and they are like this, and you find their angle will be 90. So what I'm trying to say is that the way to detect the angle between two vectors to be 90 is by taking their dot product. So what I'm saying is that if you take the dot product between two different vectors of the basis, you get 0. that making sense? Let me give you some examples so that you see better what the idea is. So if you take R2, right? That is the vector space R2, which is the plane. So what would be a basis for R2, which is orthonormal? Well, actually, the what's called like the standard basis works. So if you take E1, right? If you take B1 to be E1, which is a vector 1, 0, right? And if you take B2 to be E2, which is a vector 0, 1, right? Well, each one has length 1. And their angle is 90 degrees because one is along the x-axis, the other is along the y-axis. Or another way to say it is like if you do their dot product, right? If you compute the dot product between these two vectors, you'll get the number 0. So that means that they're perpendicular. Okay, so B1, B2 in this case would be an orthonormal basis. Form an orthonormal basis. Is that making sense? Is that okay? Any other? Now, the point is that this is not the only option you would have. There's another alternative here for, I mean, this is not the only orthonormal basis of R2. Can anyone think about another way to? Yeah.
Oh, 1 over root 2, 3 over, 3 over root 2, and that's negative 3 over 2, 1.
Well, you're, yes, let's say you were saying like 1 over root 2, right?
Yeah.
Now, did you say 3 or over root 2 or 1 over root 2?
3 over root 2.
This one?
Yeah.
Well, the thing is that this one won't have unit length, right?
Oh, wait, no, it's.
Right, you have to, it's 1 over root 2 actually.
Yeah, 1 over root 2.
So, but yeah, I mean, so another way to find an orthonormal basis would be to take these two vectors and rotate each, for example, by 45 degrees. I don't, if you think about it. So what happens if you rotate each one by 45 degrees? Like you could actually use a rotation matrix that I had drawn like some time ago. So you get a vector U1. And the rotated version of V2 would be, let's call it vector V2. U2, sorry. So what I'm saying now is that if you look at these blue vectors, U1 and U2, they also form an orthonormal basis for R2. Does that make sense? Yeah.
Does orientation matter, like how we put like B1 and then B1 of course to the right of?
Oh, in this case, no, actually, it doesn't matter how you, right, in this, right, we're not looking into that. It could also be possible to look into that, but for us, it doesn't matter. So you could also have written like, you could also have called this one U2 and this one U1 and things like that. But right, if in other contexts, you could care about that as well. And basically what you would ask in that case, like if you care about orientation, is that if you assemble the vectors into a matrix, the determinant actually gives you 1. That's a way to say that it has a correct orientation. That's a useful trick to. It's like the version of the grown-up version of the right-hand rule.
you put the vectors into a matrix, find its determinant, and if the determinant is 1, that means that the basis has the correct orientation, basically. But yeah, we don't care about that. So it could have, yeah, you could have called this one U1 and this one U2, etc. But yeah, it's a good question. But thankfully for you, we don't really care. And I think, like this rotated, I rotated it by 45 degrees. You can imagine that by any, if I rotate these yellow vectors by any angle, right, that kind of produces like an orthonormal basis. So there's kind of like a bunch of orthonormal bases, right? It's kind of I'm just trying to emphasize that again, there's not like a unique answer to the problem of finding an orthonormal basis, but it is useful to have an orthonormal basis, and I'm going to explain you why right now, unless there's like other questions before that. So why do we want an orthonormal basis? Why do we care about an orthonormal basis? Well, essentially, the biggest reason is that it gives you an easy way to express a vector as a linear combination of the basis vectors. So it gives you an easy way. So that's the answer. It gives you an easy way to write a vector as a linear combination of the basis. Of the basis vector. So what do I mean by this? I mean, I could write like a formula. Before writing the formula in general, let me just do it like with some sort of picture so that it just like that way I avoid writing like dot dot dot, which is kind of annoying, but you'll see that it kind of works the same way. So let's just say that you have like an orthonormal basis for R3. Right, what does that mean? It means that you have 3 mutually perpendicular vectors. That's like the whole point of being an orthonormal basis. So like maybe you have like B1 being here, and then B2 being here. And then B3 is supposed to be perpendicular to this one. I mean, I don't know how perpendicular they look like, but like hopefully just like you are convinced or can be persuaded that the angle between these vectors looks like 90 degrees. Like this B3 is kind of pointing towards you, leaving. So it is actually almost as if you had taken the XY axis, right? And you kind of rotate them. There could be a little bit more happening with an orthonormal basis because you're also allowed to take reflections. So you can like look at a mirror image. But if you want like some sort of like physical model, for how to think about them is it's kind of like if you had taken X, Y, Z axis and you do like a rotation of the axis. And the new axis, they give you like the directions of the new vectors that give you like the orthonormal basis. Okay. But the reason, and in this picture, you should think that each vector has size 1, right? So each orange vector has length 1. That's another condition for being orthonormal. And so the idea, right, if you had like a random vector, now I choose like a random vector in space, like in general, we typically, if you had taken these physics classes before, you would write V as a linear combination of the vectors I, J, K, that's what they call. But the point of linear algebra is that you can also write them as a linear combination of V1, V2, V3. So what I'm trying to say is that V is also like a coefficient times V1 plus a number times V2 plus a number times V3. Okay. That's what it means to say that the vector is a linear combination of the bases, right? That it's just like a sum of the basis vectors. Is that making sense so far, so good? So this is the linear combination property that any basis has, that any vector can be decomposed in terms of the basis vectors. Okay. Now, what I'm trying to say is that if these vectors are orthonormal, so if they look like this, it is very easy to get like a formula for what this constant C1, C2, C3 should be like. In general, that is not so straightforward. You would need to find like a system, solve like a system of linear equations, if you remember how to do that. But now it's not necessary. So let me give you an idea of how you would find the constants in this case. Let me single out one of these. Let me put like a color. Let's say I wanted to find the second constant. Like I want to find this constant C2, right? So what I'll do, this is like an equation between vectors. So one of the things that you're allowed to do with an equation between vectors is to take the dot product with a specific vector on both sides of the equation. So what I'm going to do is V dot C2, sorry, V dot V2 is that making sense? So notice that the going from here to here just requires dotting both sides of the equation with the same vector, and that's allowed. That's fine. Is that okay? Now, the left-hand side, I don't really know what that is. I mean, that's just like the dot product, whatever the number is, but so there's not much I can simplify on the left-hand side. But there's some simplifications I can do on the right-hand side. So that's what I mean. For some who has seen this dot product before, what's the thing that you could do with that dot product? What does that dot product formulas allow you to do?
Distribute them.
Right, you want to, I mean, yeah, one of the things that product would allow you to do is distribute it. So this is the same as saying C1 V1 dot V1, sorry, dot V2 plus C2 V2 dot V2 plus C3 V3 dot V3. Sorry, dot V2. Oops. So this is just like a distributive property. Is that okay? So far, so good. And now is where you see the usefulness of having an orthonormal basis being, I mean, this is where it's going to be used. So can anyone tell me what these two dot products should be? It's the same answer for both. Should have emphasized it. The dot product is always a number, so it's zero. It has to be zero because the vectors are mutually perpendicular. Being mutually perpendicular means that their dot product is zero. Okay, so these two become zero because the angle is 90 degrees, right? So this is like perpendicularity or orthogonality property. Okay, so of the three things that we had here in the sum, only one survives, right? Let's keep working on this side. So you have that D dot E2, right, is C2 times B2 dot B2. Let me put that in all in yellow, right? And now here I also claim that like the orthonormal basis condition gives you like the answer for what this number should be. Because now I'm asking the dot product of the vector with itself, right? So what should that number be if we have like an orthonormal basis?
One.
It's just one because remember this is the length squared of the vector, but since you're like an orthonormal basis, the length of each vector is one, so it's like one squared, which is one. Okay. Does that make sense? So it immediately gives you a formula for C2, right? So it tells you that C2 is a dot product of B with B2. Okay, so and like, I mean, hopefully it looks believable that C1, right, should be the dot product of B with B1, and C3 should be the dot product of B with B3. Right, there's nothing that really is changing like in the argument. Instead of like just doing the dot product with V2 here, you would have done it with V1 or V3 to find the same kind of like the same basic formula, just with some obvious replacements. So I'm about to write that down precisely, but what I'm trying to say here is that when you have an orthonormal basis, it's very easy to express a vector linear combination of the basis because these coefficients are just the dot products between the vector and the basic vectors. Okay. So let me write that down. So this is like this is the main reason why we're doing this. So here's like the key formula. So if V1 up to Vn is a orthonormal basis, if V1, V2 up to Vn form an orthonormal basis, and B is an arbitrary vector, then B is let me see if I
Okay. So this is the way to express a vector as a linear combination of the basic vectors. Is this making sense so far so good? Any questions about this? Okay, so I mean that's a theoretical reason for caring about orthonormal basis. Then the next question is how do you find an orthonormal basis, right? I mean in vector spaces like R2 and R3, you kind of have obvious choices because you can take like these canonical bases like the ones that are parallel to each axis. But there, I mean, as you have seen, like there are other vector spaces, like other vector spaces, like the row space of a matrix or things like that. And then you want to ask, like, how do you find an orthonormal basis for that? Okay, so there's like an algorithm or a procedure that computes on a kind of orthonormal basis, and that's called the Gram-Schmidt method. So that's what I'm going to explain to you right now. This one is kind of like a bit, I mean, the formula to memorize is kind of tricky. So I'll just like on the final, I will give you the formula for the Gram-Schmidt so that you don't have to memorize it because it, you know, it's kind of better to understand what's going on, but you know, memorizing the formula is not the objective because it's a little bit more complicated. So we're going to talk about, yeah, the Gram-Schmidt method. So, which is how to find an orthonormal basis, assuming that you have a basis for a vector space. And in fact, like if you do a bunch of pictures, it is easy to know what you should do, but we just have to think about it for a little bit. So like try to just like give you an idea of how it works. So the idea of like is that you start with the input is going to be a regular basis for the vector space, so an ordinary basis. A vector space. And the output. So you're going, after you apply Gram-Schmidt to these bases, just to make it as a diagram. So you'll apply the Gram-Schmidt, let me call this GSA, Gram-Schmidt algorithm. After you apply GSA to it, it will spit out as an output an orthonormal basis. Okay. of B. So the idea is like you started with a basis and the Grant-Schmidt method gives you kind of like a way to straighten it out so that the vectors become perpendicular to one another. Okay, while still preserving the property of being a basis. Okay, so it's just like a refinement, you know, it improved, it's like an upgrade on the basis that you started with. It just turns it orthonormal. Okay. But it actually like it's not that bad to have like an idea of how this should look like. If you do the right pictures. So let me give you what the pictures. Once you understand the pictures, like the formulas themselves are not too complicated. It's just that it's can be a bit tedious to memorize them. So that's why I'll give them to you. What makes it you know long sometimes is that it is similar to, if you remember, like the formula for the determinant. So like the formula for the determinant of a 4x4 matrix, I kind of gave it to you in terms of like determinant of a 3x3 matrix, but then the determinant of a 3x3 matrix is in terms of determinants of 2x2 matrix. So it kind of builds up on earlier stuff. So something similar happens here, where if you want to find the fourth vector here, you kind of need to know what the third vector was, the second vector was, the first vector was. So it goes like, you know, in a series of steps that requires you to finish the process beforehand so that you can continue. So like the idea, look, let me try to make a pictorial representation. So you have like three vectors, U1, U2, U3. Right, so hopefully this looks like non-orthogonal, right? Like they don't seem to have 90-degree angles between them. They have different lengths or whatever. And again, like the idea of Grant-Schmidt is that it kind of like straight makes them like a version of the XY axis in this case. So like the process in the end will, what it will produce to you is something that looks like, for example, it could look like this. Or I mean, in fact, like could be better to something like, again, we don't care about this orientation thing that someone had asked me before, but right, I want you to think about this as being more like an analog of the XYZ axis. So maybe that's what Grant-Schmidt ends up doing for you. You know, like they just turns it into perpendicular vectors. So the idea is the first one, right? What is D1? So let's start with in this picture, let's start with U1. So there's several steps. Let's say how I should say this. So it's in the first step, you just consider the first vector of the basis. Okay. So you pretend that none of the other vectors exist, right? If none of the other vectors in the basis exist, you don't have to worry about making this perpendicular to anything else, right? Because it's the only one around.
The only thing you have to worry is that potentially the length of this vector not being one, because we do want the vectors to be of length one. So there is this trick that turns, if you have like a random vector, turns it into a unit vector, which essentially is just take the vector and divide it by its length, and that guarantees that it will be of size one. So the output after step one, right? Just to take the first vector and normal, and this is sometimes called rescale it or normalize it so that it becomes of length one. Is that making sense? So, and now the idea is that you kind of forget about the original vector, and then now you work with V1, U2, U3. And now you delete, now forget about V1. Okay, and the new basis becomes is now V1 to V3 up together. Okay. So I mean, again, there are many analyses I could try to come up with. It's like if you had like n toys, right? Each of them has like a defect. So the Grant-Schmidt process is kind of fixing the toys, right? So it took the first toy, did something to it, fixed it. Fixing it, it was just rescaling it, right? And then you just throw away the older toy and you just keep the new version. But we still have like the other older toys left, right? So like that's why I'm saying like we modify the first one of the toys, but we still have like a couple more left to modify, right? So the process will be end after you modify all of them. But we're kind of looking one at a time to do the fixing, if that makes sense. So what's step two? In step two, right? In step two, now you're working with the new fixed toy and the second toy, right? Like the first new vector together with the second vector. So now you have so let's do a picture because now this is where like the picture really helps you understand what's going on. So I had the first modified vector, which is V1. And I have the second vector, right? So I'm trying to draw them in a way that's clear that there's some angle between them, which is not necessarily 90 degrees, right? So the algorithm, what it should do in this case is like, well, we'll just leave V1 untouched. We already did something to it, so we don't want to do extra work on this one. So this one should be untouched, right? But we kind of have to turn this orange one into a 90-degree vector with respect to the original, with respect to this one. So we have to kind of like, modify it so that it becomes a 90 degrees. So like that's kind of like what the process should look like, right? Like taking these two vectors, which well, in this picture had a kind of acute angle, and turn it into something that looks perpendicular. So far, so good. Now, the thing, let me make this like, let's see, what's the big name that I'm giving? Okay. So if you imagine that there's some sort of light bulb, you see that this vector, the orange one, makes some sort of shadow along the yellow one. That's actually what's called like a vector projection. And if you take multivariable calculus at some point, you'll see this. But so let's call this blue vector the projection vector. So this is kind of like the shadow, right? That the orange vector makes along the yellow vector. Is that making sense? Now, if you wanted like a formula for this shadow, right? You make a right triangle. And if you call this angle theta, right? According to basic trigonometry, right? What would be the length of the blue side in terms of theta and the hypotenuse? What would you use for that?
Cosine theta.
Right, so in like if you do cosine of theta, right? That should be the adjacent, which is the length of the blue vector, so it should be the length of this projection divided by the length of the hypotenuse, right? Which is the length of the orange vector. Okay, so far so good. But at the same time, what is the cosine of the angle? Well, let me put it this way. So I should maybe have started this. Remember what was the dot product between two vectors? This is like an aside, but what is the dot product between two vectors is, if you remember the formula I wrote at the very beginning of class, it's the length of one vector, right? Times the length of the second vector, right? Times the cosine of the angle between them, right? But what is the length of the orange of the yellow vector? It's just one because we made it a unit vector, right? So this becomes just u2 cosine of theta. So that means that cosine of theta, right, is v1 dot u2 over the length of u2. Is that making sense? So if you replace that into here, right? What is cosine of theta is v1 dot u2 divided by the length of u2. That equals the length of the projection divided by u2. Okay. And so you see like, oh, sorry.
That's the projection of V2 onto V1.
Oh, yeah, good. It was B, oops, it somehow became a one along the process, but it should have been B1 all along. Thank you. So you see like the denominators cancel, and that gives you like the formula for the length of the shadow, right? So the length of the shadow is just the dot product between V1 and U2. Is that making sense? This is why I'm going to give you the formula, because as you can see, it's kind of couple of steps. But so that's the shadow. And what's the vector itself? Well, the vector is just like, you know, a rescaled. I mean, the shadow like has length 5. Since it has to be pointing in the same direction to the yellow vector, and this one has length 1, the vector itself is just 5 times the yellow one. So what I'm trying to say is that the projection vector, this is like the second important formula of now. It's just V1, U2, or let me write it in the opposite way. U2 dot V1. That making sense? So why am I doing all of this? Because you should think that the shadow is kind of like the thing that the orange and yellow vectors have in common, right? Like that's kind of like there's like some part of the orange vector that it shares with the yellow vector, and that's the shadow. So if you want to find some a vector from here, from this picture, I mean, it's kind of maybe clear, like the stuff that they don't share is this vector that's perpendicular to the shadow. So the vector that's perpendicular to the shadow is this white one, and it actually, you know, this green vector, because of like the interpretation of the vector addition, just ends up being is basically the difference between these two. So it's just U2 minus the projection. That making sense? The thing is that this green vector may not, so this is a vector that's perpendicular to the yellow one. So the idea should be to take this one together with this one as the basis, the new modified basis. The problem is that this one may not come having unit length. So you have to rescale it or normalize it to get something of unit length. So in this algorithm, the idea is that the second vector for the basis will be U2 minus this projection divided by its length. I'll write this all again, like more precisely. So you don't have, I mean, that making sense? So, so the modified version of V2 is a lot more complicated than the modified version of V1, because V1 only required us to divide by its length. For V2, you have to compute this projection and then do the rescaling. So let me do one more step. I'll give so that you have the picture. And then probably next time we'll do is like write everything on the board like fresh, so that like it doesn't interfere with this, and then we'll do an example because it's kind of like a long process. So in step 3, so in step 3 now we have V1, V2, right? And now you have a third vector, which was U3, which is like from the previous basis. So the idea with Gram-Schmidt, again, is that like the Gram-Schmidt algorithm, let's say maybe this is how the vectors look like. Here's V1, here's V2. Now their angle is 90 degrees. That's like what the step 2 guaranteed. But U3, we don't know what the angle is with V1 and V2. So U3 maybe just looks like this. Okay. So what we want to do this, the end result of the process to look like this. So we want something that looks like 3 mutually perpendicular like axes. The person who, okay, and then what happens now? Well, you have to imagine, how do you find this V3? You have to imagine that you put again like the light bulb, right? And it makes a shadow on the plane. There's a plane that contains these two vectors V1 and V2, right? I don't know, you see it here. That making sense? So there's a piece of paper that contains V1 and V2. You put like a light bulb, it will make a shadow on that plane, right? And that shadow is called the projection of U3 along the vectors V1 and V2. That's a name that makes sense. Okay, the cool thing is that the formula for the projection is more or less an extension of this formula. So it's kind of like adding the individual shadows. So essentially to find this shadow, you just find the shadow along the first vector and the shadow along the second vector and add them together. And that actually does work. It does work because everything is being, the vectors that you had before are like orthonormal. So that kind of guarantees that you can just add the shadows like as you could have wanted. So the formula for the shadow. It actually is essentially this same formula. But instead of U2, now you put U3, so you do U3 with V1, and then U3 with V2. And again, we'll give you those formulas on the exam so that you don't have to memorize them. Okay. So this is like the shadow vector. That we care about. And then there is actually like there is like some sort of right triangle here secretly. Kind of harder to represent. And so the green vector is the one that we care about. That's kind of like the thing that doesn't overlap with the two vectors from before. So this green vector kind of by the same logic is U3 is this one minus the projection of U3 along V1, V2. But the problem is that this one may not have length 1, so you have to rescale it. And so the formula is that V3. So you're going to get V1, V2 after Gram-Schmidt, which are the same as before. You don't have to, never want to touch them. And V3 is going to be what? U3 minus the projection of U3 along V1, V2 divided by itself so that you have something of length 1. So is that making sense? So it's a bit of a mess, right? It does involve a lot of steps. So if what I will do, okay. But like the idea of the algorithm is kind of like you just try to find what the vectors share in common. What they share in common are these shadows, the shadow vectors. You delete them from the vectors in the basis, and that kind of like straighten them out or make them perpendicular to one another. But after you have guaranteed that they're perpendicular, you have to rescale them or divide them by their length to make them unit vectors. Okay, so what I want to do is like because next, like the example will take a little bit of time, so I'll do it next week. So and also like I would have to recopy the algorithm again. So next time what I'll do is just write from scratch the algorithm the way you need to know it, and again I'll give you that algorithm on the exam, so you don't have to memorize it, and it will just apply to an example so that you see how it looks like. But this is maybe the most tedious part in terms of computations of all the course, just because like there's a lot of like dot products that you have to do, a bunch of things. So it's just better to do it like from the beginning on Monday, so that you have it all like just like on the same class on the same lecture. Okay, but the idea is well, like this continues going, so then you keep going. But next time I'll be more precise and I'll tell you what I mean by that. But it is just like a kind of tedious process. But at least I'll give you an example with 3 vectors so that you see like how it looks like. After more than 3 would take for like an eternity to compute. So like I wouldn't give you more than 3 vectors to find like a basis for this. But it doesn't matter how many you have. Like could have 10 a basis vector with 10 or whatever, and it still works. Okay, but yeah, let's stop here so that like on Monday I'll just write everything down precisely. Yeah, and do an example for you to see if that sounds good.